And so you have right. So that's roughly what this picture is. So it's a more generic wormhole. So this is I'll talk a bit more about wormholes today later, but that's what the picture was.
Can I ask also a basic question?
Yes.
So if we compute this Ruta Canary in say n equals 4,
yes.
then we want to study correction to it, not 1 over n, but 1 over.
Yeah. Yeah. So this could be was part of what I was trying to say today. So let me just say it right now. So the entropy we said was area over g Newton, and so this is 1 over g Newton, and in n equal to 4 super mLs it would be 1 over some factor of 1 over n squared, right? But in n equal to 4 we are used to the fact that we have corrections which go like powers 1 over square root of lambda, right? To various powers and some number cn, right? So how do we compute these numbers?
You have it flipped.
I have it flipped. This one?
No, yeah.
Oh yeah, of course, yeah. N squared. So this is a further n squared, and then we have this power series expansion in lambda. Now notice that this, from the point of view of the bulk, so this n, so n is 1 over the coupling, 1 over g string. So all of this is classical in the bulk, should be viewed as classical string theory in the bulk. Okay. And the idea is that this should come from higher order corrections in the gravitational action. So we have an action which contains, for example, square root of gr. If we take the particular case of 10-dimensional super ML, so we'll in ADS we have an r to the 4th correction is the first curvature correction that we have. So the idea is that this first term in the action will produce an area term, and this term will produce some correction. And you have to work a little bit to see what the correction is. So let me first discuss this for the case of black holes. So for the case of black holes, it's a little simpler because the solution has a U1 symmetry, and you can give a more explicit formula. Well, the other formula has also been worked out, but it's a little harder to remember. So also for black hole thermodynamics, we'll have the same type of corrections, right? And the formula, the general formula for a general Lagrangian was derived by Wald. And the idea is that the entropy is given by so in the case of black holes with U1 symmetry, so the entropy is given by taking the derivative of the Lagrangian. So I'm just giving you the final formula just to see what flavor it has. I'm not deriving the formula, of course. So you take the derivative with respect to the curvature, r mu sigma delta, right? And then you contract with the normal binormal to the horizon, so mu epsilon sigma delta. So this is essentially an epsilon tensor in the r and Euclidean time direction. So you have the black hole will contain a circle direction. Let's label it by coordinate tau. This is Euclidean time. And then there is a point where the circle shrinks to 0. So let's call the radial coordinate r, right? So this is just an epsilon tensor of the e and r tau direction. And then you integrate this over the horizon, right? So that's the formula. And for the case of for this case, this derivative just gives you a constant. And well, this derivative contracted with this gives you a constant, and then you get the area, right? So that reproduces the area formula. In particular, the Lagrangian is a classical Lagrangian that contains 1 over g squared in front times a bunch of things, right? Times some action, so that all the terms will be of order 1 over g squared. And okay. And so you can derive this by using essentially trying to derive a formula where first consider the first law of thermodynamics, and so wrote the energy at infinity, and then consider arbitrary variations of the energy and found what quantity obeys the first law, and then in that way you derived it. Okay, so those are those corrections. A remark I could make right now is that if we view gravity as an effective field theory, there might be other competing corrections. So let's say we are in 4 dimensions. So then we have the usual term m Planck squared, or 1 over g Newton. Yeah, let me put it in terms of m Planck. M Planck squared times r, and then you can have here terms of the form r squared, right? And these terms have a dimensionless coefficient in front, right? So the correction. So if you if you think of gravity as an effective field theory where the cutoff is m Planck, right? Then this term will have a coefficient of order 1, and its contribution to the black hole entropy will also be of order 1. But that contribution is also comparable with the quantum contribution, so the loop correction, just one loop correction of the field. So the same contribution as the entanglement entropy correction we discussed before. So it would be incorrect to just consider only this correction and not consider the entanglement entropy correction, unless for some reason this one was enhanced a little bit. So in some cases it might be enhanced by logarithmic factors and so on. Now in string theory we often get these corrections with so for example in string theory we can have 1 over g string squared here, and the prefactor here is a function of g string, but in particular it contains a term that has the same order as the Einstein gravity term. So and so here the wall argument certainly would apply. But yeah, so if you are now trying to apply the argument for the case where so this is a whole series. There's another term which is of this form, right? So if now we have this term of this order, then you need to worry about at this order. You would need to worry about the one loop correction also. Okay. Okay. So that's that story. No. Yeah.
Wouldn't we be mixing effective action with loop overcounting?
Yeah. You have to be careful on how you do it. But yes. So even on what the meaning of this correction really is. Yeah, that's right. So you need to understand this properly. So my remark is that you can forget about those terms only for these classical terms. But once you get to the loop order terms, you have to worry about such things. Okay, you have to justify it a little more. Okay, very good.
So the conclusion would not be that you just consider the full effective action with respect to alpha prime and to the string, that then would follow the usual rule.
That's right. That's right. That would be too fast, and it would be an incorrect answer. Okay. Yes. Yeah. Good. So no. So the world formula was derived with the assumption of a local Lagrangian. Yeah, that was another point I was forgetting to say. So there's a question. So exercise. So let's see. Exercise. Derive formula for the entropy in string theory, right? So we don't know what the formula is. At least I don't know. Maybe one of you would. Well, maybe I shouldn't have told you that. It's an exercise, and then when someone will figure this out. But so in principle, the partition function of string theory. So there is the Euclidean thermodynamics method, which consists in computing the classical action. In string theory, the analog of this classical action is the partition function of the worldsheet on S2, right? not the particular. So that's in principle what you're computing. And then you need to take beta dd beta of this quantity. So you need to take the derivative respect to the temperature, and from there get the entropy. And in classical gravity, that gives you this local formula in terms of the area of the horizon. And here you would expect that it will give you something that involves the worldsheet, so some current on the worldsheet, and perhaps some simple worldsheet computation. This is the best you could hope for, I think. You're not going to get the area or the area plus curvature. So you're going to get something that makes sense in the conformal field theory that describes the black hole background. Yeah. And then once you have this formula, yeah, then you can. Then you find out what the conformal field theory is, let's say for ADS 5 times S5 with a black hole, well, not ADS 5 times S5, but for the black brane. And then you go from weak to strong coupling and calculate the free energy at leading order in n for values of the coupling. Should I explain that remark a little more? Well, anyway, so that's an application of the exercise. You can concentrate on this exercise. Well, you laugh, but this will be done. I mean, this will be done not some few years, but soon, maybe by one of you. Okay, so I'll like now to explain a little more. I mean, it's something probably some of you probably are familiar with, but I'm trying to explain. So we found that the entanglement entropy had a divergence in field theory, so in quantum field theory. It had a divergence which was the area over epsilon to the d minus 2, right? And in gravity, we had that it was the area divided by L Planck to the d minus 2, right? So this suggests that gravity is somehow regularizing this divergence, and it's giving us something finite, right? So that it's even suggesting a picture for where the entropy of the black hole is, which is in the fields outside the black hole horizon. And then if you went all the way to the horizon, you put the cutoff exactly equal to 0, then you would get infinity. But if you put it somehow equal to m Planck, you might get this entropy. This is what I just said is a qualitative hand-waving argument. The correct statement to make, so the conservative statement to make, is to say that this is always should be viewed as a correction, and you should never take the cutoff smaller than m Planck. The cutoff should always be taken bigger than m Planck in the formalism of effective field theory. So if you take that conservative point of view, this is always smaller than this, and you absorb this divergence in the. I mean, you could imagine that you would absorb this divergence from a counter term in the action. And, G Newton also gets renormalized at one loop. So this is the classical answer. Then you do the one loop computation. You will get renormalization. You will need to introduce a counter term proportional to Riemann curvature, and the coefficient should be equal to this one in such a way that you get cancellation. But yes. 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 The thing is that this calculation is well. So the entropy is supposed to be this plus. Yeah. Okay. So let's be a little more explicit. I will discuss this a little more in detail later. What I would like to. What I would like to do first is. So maybe you can ask your question in 5 minutes. So what I'd like to understand first is how gravity regulates this. What is different between the gravity computation of entanglement and the field theory computation of entanglement? Of course, so at the reason we got something finite in gravity is because we calculated the Euclidean action. So, for example, from the Euclidean formalism, it's very clear. So we calculate the Euclidean action at arbitrary temperatures, and then we take some derivative. We are going to get something finite. And we're going to get something finite of order 1 over G Newton because the Euclidean action had a 1 over G Newton in front. So there is no mystery from that point of view. However, we like to see it slightly more explicitly to see where the difference between the two computations is. And for that, let's imagine we're trying to compute the entanglement entropy in flat space, right? we have flat space and we have half of space. So the same picture we were discussing before when we're talking about Rindler. And when we're talking about Rindler, so we can introduce, so to calculate the entropy, we need to, so we could think about Euclidean evolution here, and we need to change the temperature a little bit, right? And for these cases with U1 symmetry, we can imagine changing the temperature by just a small amount. It would amount to introducing a defect angle there. So in field theory, what we do is we started with the metric ds squared equal to dr squared plus dt squared, r squared, n squared, right? So it's just the metric of Rindler space, where t, let's say we take t to have period 2 pi always for any n, and then we vary n a little bit. So the proper size of this circle is changing, and by taking the derivative with respect to n, we'll get the, so we calculate the partition function, log, remember, we calculated the partition function log of Cn on a space with a small conical with some small defect angle. So this is the picture for n different than 1. And then we take the derivative of this and take the limit when n goes to 1. Now, so that's the field theory computation. So this would be the field theory computation, amounts to doing the partition function of the field theory on this space. Okay, so this was field theory. Okay. Is that clear? So that's what we discussed before. Is it clear to everyone? Yeah. So now let's contrast that with the computation we would do in gravity. So in gravity, the metric is dynamical. So we can't really fix. We cannot say that we're going to compute gravity on a space which looks like this, right? But what we can say is we can fix the boundary conditions. So we can say that we have this metric dr squared plus r squared. So this is the full metric. So this was the original metric. And we can say we go up to some circle of size RC, so some cutoff. This would be some infrared cutoff in the gravity picture. And we fix the metric on that line, so on this surface. So we say that the metric on this surface is going to be RC squared times dt squared. So that was the original one. And then we fill it in the interior so that it's non-singular. So that would give us this metric. That's back the original problem. But something we can do is we can change the size of this circle, the physical size a little bit. And then when we fill it in, we are supposed to fill it in a way that is non-singular. And we can fill it in a non-singular way if we just multiply the original metric by. So if we now consider this new metric, then we fill it in a non-singular way. So in contrast with so while in field theory we got this space with a conical defect angle, in gravity we just get the circle. Okay, we just get again a circle, a smooth circle. So that's the difference between the two cases. So in the Euclidean situation, and of course from here we can calculate the partition function in gravity. So this is really a piece of the usual Gibbons-Hawking computation. So we just say we have 1/16 pi g Newton integral of square root of g r minus 2 extrinsic curvature. So this is the integral over the disk, and this is the integral over the line times rest. So the space could have some other dimensions orthogonal to this times rest. So the rest will be the area, just the area of the transverse space. Let me put it here, the area. And now consider just the line and the disk. The extrinsic curvature term comes from saying that, well, we would like to have an action defined. So with this problem with the boundary condition, we would like to have an action which is well defined so that the equations of motion are the usual Einstein equations. So, and introducing the extrinsic curvature makes sure that when you calculate a small variation of this action and you integrate by parts to derive Einstein's equations, you don't have any extra extraneous boundary terms. Okay. So this is standard. It was also figures in the Gibbons-Hawking calculation. Very good. So you have this, and now we just need to evaluate this for a disk. And for a disk, this is just the topological invariant. So, well, you can. So this R would be 0, right, for a flat disk, and K is like 1 over the size of the disk, right? And so we multiply by the size, we get the number. So it's clear that it would be a number. And well, this is a number which is 4 pi. Okay. If you can compute it, or once you realize it's topological invariant, you can take 2 disks and you get the sphere, and you calculate just this for the sphere. But anyway, so that gives a factor of 4 pi, and that reproduces, of course, the well. So we got area over 4g Newton for any n, and then we take the formula for the entropy. Recall was 1 minus n dn of log of Cn. But of course, this doesn't depend on n, so we just simply got area over 4g Newton. Okay, so that's the answer in gravity. And this is the usual derivation. I mean, not making a new derivation. This is the usual derivation, but applied just for this flat space region and for trying to compute the gravitational entanglement entropy of half a space. Now, in some sense, this, from the Euclidean point of view, this is telling us why that we don't have a divergence. So we got a divergence in the field theory case because we're doing a computation in a singular space. So if we're doing the field theory computation in a smooth space, we'd get something finite. But we did a computation in a singular space, and that's why we got something infinite. But here, we are doing the computation always on a smooth space. So gravity always chooses a solution that is smooth. Now, of course, this tells us how it works in the Euclidean case, but it doesn't directly tell us how it works in the Lorentzian picture case. So in the Lorentzian space, we have the picture in the field theory that we have a Rindler horizon. So now we go to Lorentzian signature. We have a Rindler horizon. We have the right-hand side of the Rindler horizon. And we have this gas of particles here at very high temperature as we approach the horizon. And okay, so that's infinite. How is gravity really regularizing this infinity, right? Can we say it in a more Lorentzian picture? And in Lorentzian picture, what is happening is the following. So if we have Rindler space, so we noticed that in Rindler space, we had that the temperature was equal to the acceleration over 2 pi. The acceleration is just the geometric property it's just the property of the metric, right? So once we're given the metric, we know what the acceleration is. And the temperature, well, it tells us about the state of the quantum fields here in Rindler. And in Rindler, we could imagine taking a temperature different from the acceleration. Of course, that would produce a singularity on this surface, but we could imagine taking it different. And that's what we do when we calculate the entropy. So we take the temperature slightly different than the acceleration. But in gravity, what is happening is that we start with something like Rindler. We try to change the temperature away from the acceleration, and the geometry moves, or the horizon moves, in such a way that the temperature becomes equal to the acceleration again, right? So that's the statement that the geometry is smooth at the origin, right? So in some sense, and this you can view it as a slightly more Lorentzian version of the mechanism, so something we can say is that people in the past said that nature abhors a vacuum, so nature hates a vacuum. That's why things rush into field in the vacuum. But we could say now gravity really allows only the vacuum. So gravity really only likes the vacuum. We could try to take the fields away from it in a singular way, and it doesn't allow that. Now, one would have to like a more explicit formulation of where the black hole entropy is coming from. And we definitely have from string theory some very concrete descriptions of black hole entropy, but they are not local in the sense that they don't come from integrating over. In particular, the descriptions we have of this in string theory do not come from a regularized version of this integral that we would do in field theory. It's a much more indirect way of calculating the entropy. And we could discuss that in an extra lecture, perhaps, how to get black hole entropy from string theory. But all the derivations come from, well, looking at the system from far away, from a boundary, perhaps, and finding a description for the whole space-time and so on. But we don't have a local description of where the entropy comes from. And if we had it, then we probably would be in better shape to answer other questions of black holes, information paradox, and so on, if we had a more local description. So maybe there isn't, and maybe black hole entropy always has to be described in a non-local way. So that's one possibility. Okay, higher derivative corrections I already discussed. So let's see. That's the next topic. Quantum corrections. Okay, so let's discuss a bit quantum corrections. We discussed them a little bit. Let's discuss them a little more. So we're now going to try to discuss quantum corrections to black hole entropy. So first, the simplest way.
Yeah. That, if I understood correctly, you were describing the usual black hole entropy, right?
Yes.
But the correction to Ruta, my question was about the correction to Ruta Canary.
Yeah, sorry. Oh, yeah, I forgot. Yes. So the correction to Ruta, so in Ruta Kaganagi is equivalent to, ends up being equivalent to considering this kind of Euclidean computation for a situation that is not U1 symmetric. So there is some circle that is basically very similar to before, but the circle doesn't have the U1 symmetry. And in that case, you can use this replica trick that we discussed before, and you can do Euclidean sort of a generalization of Euclidean thermodynamics, but now using this replica trick. So you well, let me just first give you one sentence. The answer is that it is not the same formula, and it's a formula that includes extrinsic curvatures. So extrinsic curvatures of the surface, and it's slightly more complicated.
It does not reduce to this one in the case, or
yes, in the case with U1 symmetry, it reduces to this one. Yeah. So the extrinsic curvatures of this surface are tensors that have indices in the two orthogonal directions, right? And if you have a U1 symmetry, then they have to vanish. Okay. So good. So now let's discuss quantum corrections. Yes.
I don't know if it's a good time to bring up the question.
Yes.
How does this resolution relate to the interpretive argument you gave?
It's totally, it's unrelated. We'll now discuss your question. Yes. Yes.
So if the main reason we get the divergences
yes.
is that we have these singularities,
yes.
how do we know that it's just not like weird happening when we take the limit as n goes to
well, you could say that this is somehow a little unphysical, having to do with the singularity, and we should not consider these divergent contributions to the entropy, and we should only focus on the finite parts. So you could certainly say that. Mm-hmm. So I won't complain if you say that. But yeah, it's interesting that if you naively add this entropy, you get something that has the same structure. So people for a long time thought that we would get the black hole entropy in this way, and people said this before there were any results of black hole entropy in string theory. And once we understood how then one can compute black hole entropy in string theory using BPS black holes or ADS-CFT, and the computation doesn't look like this. It's a completely different computation. Right. Yeah. Yes. Well, here, I mean, we would have matter fields which are so we had flat space, so we have some constant matter fields. They don't. Well,
I guess it's confusing.
The,
It looks like the contribution of matter fields on that geometry is very different
yes. I'll try to maybe ask me the question in 5 minutes. So. Maybe I confused you a little bit. So I discuss here two different computations. One is field theory computation, and the other one is gravity. And I try to point out what the difference was between the two. Why one was finite and why the other one was infinite. Okay, I'm not saying one is equal to the other. I then vaguely said that maybe there is some relation, but I didn't offer any concrete relation. So now I'll try to relate them in a logical way, but it's still not answering the vague. So we are going to consider quantum corrections to black hole thermodynamics. So Euclidean black hole thermodynamics is based on considering the metric of the Euclidean black hole for arbitrary beta, right? And then we calculate the log of the partition function of full gravity theory on this geometry, which can be expanded. It will have a classical action. So this is the classical action, which is a function of beta. So this comes from integrating 1 over, well, something of the form G Newton, R, curvature, and so on. And then we have a one-loop correction that comes from the one-loop determinants of all the quadratic fluctuations of all fields on this geometry, including the graviton and scalar fields or whatever other fields we have. So let me write this as log of determinants. Roughly speaking, of course, if it's a scalar field, there are factors of a half and so on. So this is the full computation, and of course, this log of determinants are infinite, and you need to regularize them. So by this term, I also include the subtraction of any counter terms that we can have, right? So we'll have integrals of counter terms. So there will be 1 minus epsilon to the 4 square root of g plus some terms 1 over epsilon squared r and so on, right? So this regularized with cut of epsilon, and then we have this whole thing. So this whole thing is supposed to be finite, right? Right? Finite for any beta. Okay. Is this clear? I mean, these powers of epsilon are the ones for 4 dimensions. Of course, in other dimensions, we might have more counter terms. And then you can calculate the entropy. So the entropy is, well, this formula we have seen many times of the log of C of eta. And, well, you'll get a classical piece, which will come from the classical action. Which, if you take the action is just this, we'll get the area divided by 4g Newton. And then we'll get something that comes from taking the derivative of this. So whatever we get from taking the derivative of this is going to be finite, right? This was finite for any beta. We take the derivative, we still get something finite. Okay. Now, we can decompose that finite thing that we get into a sum of pieces. Okay. So we can take first the derivative of beta d beta of this quantity and then of this quantity, right? And what that so that will give us a bunch of a sum of the various. So we're going to now take these derivatives by parts of the various terms, and we'll get the sum of terms that will be separately infinite, well, separately divergent. So we'll get one piece that will be the entanglement entropy outside from taking partly from this, well, essentially only from this. Then we'll get a term that I'm going to write as minus. So a term from here, area over epsilon squared, right? So this term will not contribute nothing, and this term. So these terms have the same form as the original classical action. So when we calculate the action for these terms, we'll get the same form as the original one. So we'll get such terms. And then we'll get other terms, which are like something like delta area over 4g Newton plus delta, let me call it as wall-like expectation value. So I'll discuss these terms in So first, let me just say something simple. So this term had some divergences, and then they will be cancelled by the divergences we got from here. So the divergences cancel. Then there are these other finite terms, and I'll discuss them now one by one. So the main thing to say is that here the main qualitatively new term is this one, because this is going to be a non-local expression, comes from some kind of determinant and is integrated over the fields outside the black hole horizon. These two other terms will be evaluated on the black hole horizon, can be with a small correction to something similar to what we had before. Okay, so when we calculate 1 minus beta dd beta of log of the one loop determinant piece of log of that, right? So this is the one loop determinant. Well, we could put C one loop. This derivative really contains two parts. One is it's just that we are changing the period of the time direction, and the other one is that we are changing the metric. So the black hole metric changes because it has to change in order for the circle to contract in a smooth way at the origin, right? So let me be, well, was this is understood, or should I explain it more? Yeah. Yes. No, this is the counter term you need. So first of all, the counter terms are only due because to the fact that we're doing a one loop correction, right? So we have the classical action, then we have the one loop correction. No, the classical action, the action we started with. So we start with some classical action. We keep this finite. This will contain some divergences, and we just simply, when epsilon goes to 0, we subtract those divergences. Is that? Yes, there is. Yes, there are such ambiguities. No, well, these are uninteresting ambiguities because the whole thing is. So you do it whatever way you want, and these finite ambiguities correspond to finite shift in G Newton. Since in the very beginning you didn't know what G Newton was, so you could just shift the original value of G Newton. If you started from some theory where you know for some very specific reason what G Newton was, then maybe it makes more sense to consider, to understand those finite shifts. But in general, from the point of view of an effective field theory and so on, it doesn't matter. So the most practical thing is to just say you subtract everything, and that's it. Okay, so what was I saying? Yeah. Right. So we'll have the change in the period of the coordinate and that. If we only change that would correspond to doing the partition function on the black hole metric, where we introduce a conical singularity. So we took the original black hole metric and we changed the period of the time direction. So we do only that. We get a singularity at the black hole for non-zero for a different beta, and when we take the derivative, we get the entanglement entropy. That's the standard calculation, the same calculation we were doing in the field theory, right? Computing the partition function on a space with a cone. Right? So this piece is the S entanglement. And then there is the explicit dependence of the metric of the black hole, and this has the form the integral of d mu nu beta dd beta of g mu nu. Okay. So this is the quantum expectation value of the stress tensor due to the one loop corrections. So let's say for simplicity, let's fix the classical t mu nu to 0. And consider fluctuations around, let's say, a Schwarzschild black hole, where nothing has an expectation value. Then, due to quantum mechanics, it might happen that you get the quantum expectation value for the fields, right? For example, with the Casimir effect, you do get such an expectation value. And since the black hole, let's say, very far away looks like a cylinder, you certainly expect something like this. So you expect a term of this form. And this is the explicit dependence of the metric on the temperature. So if you had a Schwarzschild black hole, this would come from changing the mass of the Schwarzschild black hole, that we need to change the mass when we change the temperature. Okay. So that's what we get from here. And this term, so this whole expression, I won't explain in detail, but can be understood as what I wrote over there, delta area. Turns out that is equal to delta area over 4g Newton. So you need to use the Einstein equations of the bracket and so on. Now, delta area, what it means is the following. So we had the original Schwarzschild black hole, which was a solution with 0 stress tensor. But now we have this quantum mechanical stress tensor, quantum mechanical generated stress tensor, and we'll need to change the black hole solution. And the new black hole solution, the area for this particular temperature will be different. So that's the delta area. Of course, the change in the area is of order g Newton. So this is of order 1. Okay. So this term is also of order 1 in the same. That's of order 1 in the g Newton expansion. So they're all independent of g Newton. And the last term is something you can forget about in the first approximation. But let me give you an example where such a term arises. Is if you had a term in the action which had a coupling of this form. Then let's say phi is 0 in the original background. So this term is not contributing to the entropy in the original background. But you could have, however, if we formally calculate the Wald entropy formula through the formulas we were discussing there will be an additional term proportional to phi squared. And then that term corresponds to take the quantum expectation value of phi squared, which might be non-zero, could have even a finite piece. There will be a divergent piece, and there could be also a finite piece. The divergent piece also should cancel for generic reasons. Okay, so those are the various terms. These last few terms are not too important. This one is a little more interesting because it's a qualitatively new contribution. And well, that's the story. Okay, so people had questions. Now there's the time. If I didn't answer them, it's time to ask them again. Did I answer them? Or yeah, you also I think had a question. Or who else? Pedro, I think. No. Ah, okay. Okay, good. I'm going to skip this. Let's see. So now we'll discuss quantum corrections to the Ruta Canary formula. Well, let me just make a simple. Yeah.
Do you also have a way of understanding this kind of correction? Way that you
yeah. So again, in string theory, you would have to compute the one-loop diagram. So the classical one would be just the sphere diagram in string theory, and the next correction is just the one-loop diagram. Yeah, in principle, you could compute this one-loop corrections. For the case of the BTC black hole, we did compute these one-loop corrections in a paper with Johnson and Hiroshi Oguri. But yeah, so you can compute them. Okay, so right. So now quantum corrections to Ruta Canary. Before I go to the quantum correction, so there is one little thing I wanted to mention here. So if you really want to compute the quantum correction to the black hole entropy, you really want to get the number. You want to get whether it's pi or 3 or whatever. It is simpler to do it in the Euclidean method typically. You get something finite directly. You don't have to worry about these different pieces. The reason I discussed this is just because this piece has this interesting interpretation, and we used it before also, right? So that's why I was discussing it. Another thing I should discuss is that I should mention here is that sometimes these one-loop corrections sometimes have some logarithms, have some large logarithms. This is especially the case when there's a logarithmic divergence here. So those logarithms are typically easier to compute than the full determinant, the full number, because Sen, for example, computed those and matched them between microscopic entropy computations and macroscopic computations of this kind. Okay, so now back to quantum corrections to Ruta Canary. And before saying what it is, let's start with a simple paradox. So imagine that we have a spatial direction, right? And we consider two intervals that are separated by a very long distance. Then in this case, the entanglement entropy of A is given by this, the entanglement entropy of B is given by this, and the entanglement entropy of A and B is given by some surface which starts and ends on these two boundaries. In principle, is two lines that go between here and here, for example. But you can reconnect them and then make them equal to the two lines that we had in the beginning. And so the entanglement entropy of SA, so SA union P is equal to SA plus SB. And if you remember the formula for mutual information, which was SA plus SB minus SA union B, this implies that the mutual information between A and B is actually 0. Okay. So this is only true. So this is true with the Ruta Canary formula, which is proportional to the length of this formula of this geodesics in this case. But recall that there was a bound saying that this mutual information is less or equal than any connected correlator that we can have between A and B, right? Some formula roughly of this form, right? So how can this be correct? So the important point here is that the correlators that are non-zero, so are correlators of, let's say, some gravity modes, which are of order 1. They are not of order 1 over g Newton. Okay? So really, to check this, we need to understand what these entropies are to order 1 over g Newton. Now, if you follow the derivation, so one can derive the Ruta Canary formula from the rules of ADS-CFT. And if you follow that derivation and you to one loop, so you get something very similar to what we were discussing here. And what you end up with is that the entanglement entropy of region A is again the area, so that's the classical piece, plus the entanglement entropy of the entanglement entropy in the case of black holes was entanglement entropy outside. In the case of this Ruta Canary discussion, is the entanglement entropy of these regions, right? So the region that is, so if we have an interval, some region A, we have the Ruta Canary surface, so the region that is between the interval and the surface, right? Which in some sense is the region exterior. So if you view the surface as the horizon, analogous to the horizon of the black hole, so it's the surface outside the horizon, right? So let me call that A bulk. So it's the bulk region connected to A. So it's the entanglement entropy in the bulk of this. So we consider the fields in the bulk. So now we have quantum fields in the bulk, and there is some entanglement of these quantum fields between this region and the rest. Okay. And so now, if there is a non-trivial. So in this case, when we consider as A union B, it's not just the sum of these two entropies, but it's actually a bit bigger because there could be entanglement between A and B, right? They're just given by the bulk. And so just simply the properties of field theory in the bulk ensure that this will be obeyed because we are treating the bulk as a field theory, and this was a general result we derived from field theory. I mean, this inequality, of course, and this will be non-zero. The right-hand side will be non-zero. Okay. So that's okay. Of course, we also would have those other corrections that delta A, etc., that we were discussing before. But all this will be integrals over the surface, right? So for the same reason, so the mutual information coming from these pieces will also vanish for the same reason that the area was vanishing. So, well, we could still add them, and to have a proper formula, we should also add them. But if we are interested in finding the qualitatively new effects, we would want to compute it. We want to add it. So in particular, if you had a spin 1/2 here, a spin 1/2 particle entangled with another spin 1/2 outside, you will get a contribution from this term, right? So it will not come from the gravity term, but it will come from this term. Okay, so now let's discuss the discuss the eternal black hole a little more.
First two terms are the only ones that are more or less reversible. And the rest is
Yeah, the rest is not known. Yeah, how to compute in a simple way. Yeah.
This one should get away just with Euclidean space.
Yeah, so this is all these computations are using the bulk effective field theory. You don't need you don't need to do string theory. But if you had a situation again with a low string scale, then you would want to do it using string theory. Yeah. By string theory, here we are meaning perturbative string theory, just classical string theory. Yeah.
Do they hold as well for
Yeah, covariant entanglement. What's the covariant?
time?
Good. Yeah, so the derivation of the original of just even the Ruta Canary term for the time-dependent piece was not done. So, and so people are thinking about that, and maybe you could do it. I'm not sure. But once you do that, perhaps you would also get in a simple way the other one. Yeah. So the derivation of the original one is for situations that have a time reflection symmetry. That's the one we've given. Okay, but it's probably also true. So now we'll want to discuss the eternal black hole. So this is the eternal ADS black hole has a Penrose diagram of this form. So here, this is the ADS boundary. So the geometry of this region can be drawn as so we have the boundary region and we have a black hole inside, right? So that's the spacetime. This is a spatial slice, let's say, through here of the geometry outside this black hole. So this is the left. This is the right exterior. Exterior right. We have some exterior left here. And then, so this is a second ADS space with a black hole in it, completely separate from the first one. And these two black holes are connected through the horizon. So if you go, you are 1 meter outside this black hole, 1 meter from outside this horizon, you are 2 meters from each other. And then you have the interior. The important property is that the interior is shared between the two black holes. And the question is, the first question is, what is the field theory interpretation of this geometry? Or is there a field theory interpretation of this geometry? And to understand that, it's useful to think about the analytic continuation of this two Euclidean space by taking this spatial slice, which has a time reflection symmetry. And if you have any situation that has a time reflection symmetry, you can continue time to Euclidean time on the bottom here. And let's say we can think of a picture of a kind of half Lorentzian, half Euclidean, where in the bottom you have half of the Euclidean black hole, which so recall that the Euclidean black hole is a full circle. So the circle is the time direction of length beta, and then the fact that it shrinks in a smooth way is just saying that the topology of this, that the radial direction in the circle is just that of a disk, right? And that's what we are drawing here. So this point here, r equal to 0, is the horizon. So this is the horizon. In Euclidean space, that's just the origin. It's a completely smooth point. And so we can think of, when we cut here, we can think of this Euclidean evolution as preparing a state. Recall that even in flat space, we think of Euclidean evolution from minus infinity in Euclidean time to 0 as preparing the ground state wave function. So here we can similarly, in the bulk, think of this as creating the state here at t equal to 0. And also on the boundary, so we can think of this Euclidean evolution on the boundary as creating a state, but the state now is in the product of two separate disconnected field theories, right? So these field theories are connected through Euclidean time, but are otherwise disconnected once we go to Lorentzian signature. Okay. So then this this picture tells us what state we should be considering, and the state has a name which is called the thermofield double. Was a state that was considered in the context of analyzing thermal field theories. So state psi. So this is a state in CFT left times CFT right. So a state in the direct product of the two Hilbert spaces. As I said, it's called thermofield double, and has the form. So you sum over all eigenstates of the, let's say, left field theory with a factor phi to the minus beta e over 2. So this is half of the usual Boltzmann factor. And then you take En for the left theory and En for the right theory. So basically we take a whole basis of states labeled by n. So we take all states. And we take the same state on the right and the same state on the left. And we put these Boltzmann factors. The bar means here we get the time reversal and charge parity conjugate state. I mean, it's related to the fact that the way we get this state is simply by evolving. Let's say we get the identity here. If we were to cut a very tiny space, we just the identity, right? We sum over all states, and then we just evolve using Euclidean time, and we get this state. This 2 comes from the fact that we are considering half of the circle, and this state has the property that just define exactly the way it's defined here. The norm of the state would be the partition function, or more precisely, since the norm can be set arbitrarily, the idea is that if you take operators that depend only on the right, and you compute the expectation values on this of these operators on this particular state, you get thermal expectation values of all right. So trace over h right of rho thermal. So this is the thermal density matrix for the right part, and so on. Right? And for this reason, it was considered in the past. So some Feynman rules and so on are simple if you slightly simpler if you think in terms of the thermofield double. Okay. So the idea then is that this geometry really corresponds to this thermofield double state, and this why is that the case? Is simply because we got both the geometry and the boundary state by doing this Euclidean continuation and cutting the Euclidean diagram. So we got them from the same construction, both following the same construction both in the boundary and the bulk, and therefore we would think that they have to be the same. Okay, so that's the argument that they are the same. But this is rather peculiar because we have a space which is connected through the interior, but we had two states that were completely disconnected in the boundary theory. So now for this interpretation to be correct, it should be the case that you cannot send the signal from the left CFT to the right CFT, right? So imagine that it was possible to send the signal from the left to the right. Then the ability of sending a signal will imply that the commutator of the operator that sends the signal with one that receives it, it's non-zero. So we would have a non-zero commutator. But that wouldn't be possible if the states are just purely entangled. Or in other words, you know that we cannot send the signal using entanglement, right? So entanglement means that you have correlations, but not cannot be used to sending signals faster than light. Okay, and so in this particular example, we see that we cannot send a signal, because if we try to depart from here, we'll get to the singularity and we'll not get to the other side. So indeed, it's consistent. This interpretation is consistent. But not only that, but in any situation where you have these Lorentzian wormholes, so for all Lorentzian wormholes that have ADS regions far away, you can prove from the null energy condition implies that there are no signals. Now I'm calling this a wormhole because so here we have a sphere, which is this sphere that is shrinking as we go in the radial direction. It reaches a minimum size at the horizon, and then it expands again on the other direction. So the spatial geometry on this slice is really a wormhole. So it's something like so we have some ADS space, and we connect the two sides in this way, right? So these two regions are asymptotically hyperbolic in this case. Okay. So GR allows us to have wormholes, but we cannot use them to send signals. And the fact that you cannot use them depends on this null energy condition. So it's a somewhat non-trivial property that it all works out so that you cannot send signals. It's even more interesting if you realize that, so null energy condition means that T++, so the classical null energy condition is that T++ should be bigger than 0, right? So the plus component of a stress tensor should be bigger than 0. Or more invariantly, the contraction of T with a 2 with the same null vector. Well, anyway, it's obvious. Now, quantum mechanically, you can have. So I'm now going to make a small digression on these null energy conditions. Quantum mechanically, you can have that T++ at a given point might be less than 0. Okay. So, and in general, it will be less than 0. So you can very easily construct a state where the expectation value of T++ in that quantum state is less than 0 at some point. Okay. Now, if you were in flat space, now if you integrate over dx plus, well, let's say you integrate over dx plus T++, then this now is bigger or equal than 0. It's not terribly obvious, but you can make some arguments that in general this should be bigger than 0. In free field theory, you can check that this is bigger than 0. So if you integrate between minus infinity and infinity of dx plus T++, then that's bigger than 0. If you also integrate over the transverse dimensions, this is just also P+, which should also be bigger than 0. Okay. Okay, so now what? So because in quantum theory sometimes T can be less than 0, you will see in the popular literature that quantum mechanics allows wormholes, and you can travel faster than light, and maybe and so on. So we can go from GR allowed wormholes to science fiction wormholes, right? Okay, but the null energy condition. And they say, well, classically it is true that they are not allowed, but we could have a quantum. According to quantum mechanics, it's allowed. However, people have extended these theorems where the only thing you use is the so-called achronal average null energy condition. Sorry for being a little technical, but since this is a point that always there are many people who claim to have wormholes that allow traveling faster than light, I like to explain where the negative statement comes from. Now, the average null energy condition is that you integrate along the. Imagine you have this null. You take a null line here, and so you integrate T++ along the null line. Okay, so that's what average null energy condition. Now you might think that based on this flat space example, you might think that this is always positive, but it's actually not always positive. And we can give an example. If we consider, for example, a cylinder, the Casimir energy on a cylinder is negative, and we computed the other day that T++ is minus C over 24, right? So if you integrate it along a null line around the cylinder, so you will get something negative, okay? So it's actually not true. But achronal means that you cannot send a signal from a time-lag signal. There are 2 points along the null line we're considering are not time-lag separated, as they are here. So here you can find 2 points which are time-lag separated, right? So this is not an achronal line. And for achronal, this null energy condition seems to be true in quantum field theories, and no one has found a counterexample to this. And it is, and you can find sort of proofs from, for example, in theories that have holographic duals. This is true, so this is believed to be true. So this whole condition, and if you assume this condition, then you don't have traversable wormholes. Okay, so you don't have science fiction wormholes. Is there any question? Yeah. Yeah. Mm-hmm. Well, that depends on how we realize. So the operators so here when we talked about entanglement and so on, it refers to quantities we can do in the field theory, right? So to field theory quantities, and so well, that's a good question, and so I would say it has to from this picture. But there's some discussion. So some people say that it doesn't. So some people would like to claim that this picture is totally wrong, and here you should have some fastballs here and some fastballs here, and you should have no interior. So when I said that particular thermofield double corresponds to this particular geometry, that was based on this argument. There isn't nothing more than this argument. And so you would have to explain why this argument is incorrect. So people who want to advocate for no interior and firewalls and so on would say, well, perhaps in this argument you create by tunneling lots of fastballs. But there's nothing clear that's been said. Let's say. I don't believe those arguments. I don't believe any argument saying that this is wrong. Some other people want to have it both ways, say that, well, I'll discuss. Well, maybe I should discuss it now. So some people say, okay, so here in this particular case of that thermofield double state, you have some kind of connection. But as soon as you consider more generic states, you will not have any sort of connection, right? And you would have a firewall behind the horizon, just behind the horizon. So those people, I guess Joe will advocate that picture to you later in the week. So the picture there is that the dual of the generic entangled state. So now, the idea is that depending on, you can have, so here the density matrix for the right, observe the right side is e to the minus beta h, right? And the same for the left side. The same e to the minus beta h right and h left, okay? Now, just only giving these density matrices doesn't tell you that the dual is this geometry, right? The dual is this geometry only if you have that particular entangled state. You could change the entangled state, keeping the density matrix the same, right? So you could, for example, act with a unitary operation on the right, right? So if you act with a unitary operator on the right, you would change the entangled state, but you would not change the density matrices, right? Yeah, what do I want to say? Yeah, so what these people want to say is that if you took a generic entangled state, then the picture would be So the same exteriors by some kind of firewall here. So something that when you cross it, you die exactly at the horizon and not a little later, right? So the whole discussion of the firewall is really about the afterlife. So if someone sees you dying here, would you really die here or experience a little bit of an afterlife later, right? So that's what the whole discussion is. And so, but I don't feel, what?
It's not a little bit, it's a black hole.
Yeah. So it's a distance. Well, it is true. So if the black hole is very large, it's not very big. It could be very big, so it could be a whole more than your lifetime. And of course, understanding this is important. Well, I guess Joe will explain why it's important to understand this. Because if you really understood the interior of a black hole looks like a cosmology, like a collapsing cosmology, an isotropic collapsing cosmology. So if you really understood the interior of the black hole properly, you perhaps will understand time-dependent backgrounds better, and you'll understand how to think about the interior. So I was asked before whether what the operators in the interior, what was the description of the operators in the interior. And so in this particular case, we can give a description by saying we have the operator here, and we just evolve it using the bulk equations of motion to this slice. And with this slice, we use some dictionary to express it in terms of. So we solve somehow the equations of motion sideways to relate it to the operators here on the boundary on the two sides. So an operator in the interior would be some operator acting both here and here. And that's the description for these operators in this particular case. That's the best description we know for those operators. Yes. Yeah, I mean, this operator could suddenly receive a signal from somewhere here and here, or this operator here could send signals here. But this is not surprising because we are acting on both sides, right? Okay. Now, just one more remark about wormholes. I was told I could go on forever, right? What? Okay, good. Yeah, a little more about these wormholes in the case of Schwarzschild. Right, of course, the Schwarzschild, eternal Schwarzschild is the same diagram. And it's really the simplest solution that is spherically symmetric of GR, right? The simplest non-trivial solution, so we would like to understand it. And the idea is, again, that it's an entangled state of black holes in two separate universes. But there's a closely related state which would consist of two black holes in the same universe, where, you had the original. So here, if you look at this slice, as we discussed before, would connect two flat spaces, in this case, through this neck. This is sometimes called the Einstein-Rosen bridge. Einstein and Rosen in 1935 or 6, they noted that they wrote Schwarzschild metric in some coordinates where they could see that this slice went from one universe to the other. Their object, they were not thinking about entanglement. Well, they were actually thinking about entanglement because later they wrote Einstein-Podolsky-Rosen, but they didn't say that this had anything to do with entanglement. They really were motivated by trying to find a geometric picture for particles that would be non-singular. So, kind of classical physics idea. Anyway, so you have this, and these are two black holes in completely separate universes. But here you could consider two black holes in the same universe, and as long as they are really far away, they're going to be more or less the same as this. At least the metric in the neighborhood of each horizon is going to be described by this region of the diagram. And you can actually even find solutions that do this, so it's no problem. They do exist as solutions. So here we have two observers, one here and one here. There is a long distance between them, and then there is a short distance through the wormhole, right? A spatial distance through the wormhole. So here, the short spatial distance would correspond. So we have these two guys, and they are separated by a short distance. Now, as long as these guys stay outside, they cannot send a signal through the wormhole for reasons we have discussed before. But one thing they can do is they can jump inside. So if this person jumps inside, then he can receive the signal from this one, or they can even meet in the interior, right? So if you have, let's say, this black hole could be in. So we have Romeo and Juliet, right? Which their families didn't want them to meet, so they put them really far away. But they make themselves, they send each other a bunch of qubits, and they construct two perfectly entangled black holes. And then after they do all that, then they can meet. Okay, they can jump in and they meet. And their families didn't know. They just see them jump into the black hole. They would see them dying. It's exactly what Shakespeare wrote. They died, but maybe they actually met. Now, why is this geometric connection somehow relevant for some of the... Well, now I'll discuss something perhaps related to the firewall paradox, and given that Joe will talk about that, that's a little acausal. Well, these remarks... Well, maybe I skip that. Well, yeah, maybe I'll say it. Okay, so what is the firewall paradox? So let me... one version of it. So there are sort of four versions. Joe likes to say that it's all the same argument, but I like to say that there are four arguments. So there is paradox number one has to do with entanglement and uses the strong subadditivity condition. And this paradox is the following. Suppose that you have a black hole, right? So has a certain number of microstates given by the entropy, right? Imagine that this black hole is entangled with some other system. So this is some other reference system. So let's say it's maximally entangled with the reference system. One way you could consider this happening is by you start out with a very big black hole, and you let it evaporate it until it becomes this very much smaller black hole. And the initial black hole was so big that it was initially in a pure state, and it emitted radiation, which it looks like it's completely random. And so at the end of more than half the evaporation time, or more precisely after more than half of the entropy was emitted of the original black hole, you will have that final black hole should be maximally entangled with the early outgoing radiation. So in that example, this reference system was the early outgoing radiation, but we are not going to necessarily assume that. Okay, so this could be the early radiation. So maximally entangled means that if you look at the Hawking mode, one mode that will be emitted later, let's call this mode C. Okay, this will be sort of maximally entangled with some qubit. So think of this as a qubit degree of freedom. This would be maximally entangled with some qubit degree of freedom in the radiation. So radiation is going to be it's not going to be easy to extract this single qubit that is maximally entangled with this qubit outside in Hawking radiation. It's going to be very difficult to do that. But in principle, you could take the early radiation and make it go through a quantum computer that can do such things, and extract the qubit B that is maximally entangled with C. Okay, so this line.